Welcome back to the deep dive. This is where we take complex fields, grab the sources, and really just give you the essential knowledge fast. Today, we are strapping in for a deep dive into cryptography, the science of, well, secure communication. You give us a fascinating stack of materials on this, covering everything from these ancient secret codes all the way up to, current quantum threat models. So our mission is to distill that core evolution of the field for you.
It really is an evolution of trust. I think for most people, cryptography is just about hiding messages. But the scope of modern digital security, it requires so much more than just confidentiality.
Okay, so let's nail down those expanded goals right at the start. If it's more than just secure communications, what else are we asking it to do?
Well, we really rely on it for four key functions. Yes, the first is still confidentiality, secure communications. But just as crucial is authentication. And this has two parts. You've got entity authentication, which proves the person on the other end is who they say they are. And then data origin authentication, which verifies the data itself hasn't been, messed with since it was sent.
So proving identity and proving message integrity. That makes perfect sense for things like financial transactions.
Exactly. And the final piece, which is critical for all commerce, is non-repudiation. If Alice authorizes a transfer, cryptography has to provide a mechanism so secure that she can't later deny sending that message. It just locks down accountability.
Okay, that sets up our deep dive perfectly. So we're tracking the historical progression of how security is even achieved. We start with systems that required keeping the whole method secret, then move to systems where you only needed the key to be secret. And today we rely on mathematics, basically betting that decryption is just computationally infeasible for any adversary. So let's start at the true beginning, the classical ciphers. Every discussion starts with the Caesar cipher or the simple shift cipher. It's elegant, it's historically important, and yet it's just fundamentally insecure.
It's the perfect foundational example.
Yeah.
Julius Caesar would take each letter and shift it forward by a fixed key, $K$, a simple substitution. But the catastrophic flaw, as you know, is the size of the key space.
Right, because in the Latin alphabet, there are only 26 possible shifts. You don't need computing power. You can break the entire system with pen and paper in minutes through exhaustive search.
And if you have a message that's long enough, you don't even need to search all 26 keys. You just use frequency counts. Since the letter E is the most frequent in English, you find the most frequent letter in your ciphertext. That one piece of statistical info immediately reveals the shift, and the whole message just unravels.
People figured this out pretty quickly, realized the shift cipher was too weak, and then tried to generalize it, moving to affine ciphers. And this is where the math starts to impose some real constraints.
Yes. The affine cipher uses the formula 6 ducks or right arrow acts plus BP mod. This looks like a simple step up, but if you select the wrong value for that coefficient A, the entire cipher fails completely. For example, if you chose, say, $1,300.
Why does choosing a 1303 break the system?
It's a crucial insight into why math underpins all of this. For the cipher to be invertible, meaning you can actually decrypt it, every plaintext letter has to map to a unique ciphertext letter. If $1,303, several different input letters all map to the same output letter. You can't uniquely reverse it. Decryption is impossible. The system has to be one-to-one, and that means mathematically, I has to be co-prime with 26.
That's a huge leap from simple shifting, but frequency analysis could still eventually take those systems down. The real challenge to cryptanalysis came with the Vigenère cipher, which used a keyword to create a polyalphabetic system.
The Vigenère cipher was a revolution. Because the shift changed with every single character depending on the keyword, the letter frequencies were completely diffused. They called it le chiffre indéchiffrable, the unbreakable cipher for centuries.
How did cryptanalysis eventually counter something so clever?
They attacked the structure, not the key. The breakthrough was finding the key length. Cryptanalysts look for repeated segments of, say, 3 or 4 letters in the ciphertext. That suggests they were encrypted using the same part of the repeating key. More formally, they'd use the index of coincidence, which measures the probability that 2 randomly selected letters are the same.
And a high probability means you've shifted the text correctly, isolating a key period.
Exactly. Once you find that the key length is, let's say, 5 letters, you then break the entire ciphertext down into 5 separate streams. And each one of those streams is now effectively just a simple Caesar cipher. Frequency analysis works perfectly on those 5 smaller chunks. The polyalphabetic system is just reduced back to the weakness of the classical ones.
This is where it gets really interesting, showing how powerful deduction can be. Your sources had that brilliant anecdote of Sherlock Holmes and the dancing men.
hmm That case is a masterclass in solving a simple substitution cipher using pattern recognition, not brute force. Holmes had very little data, but he combined language structure guessing flags meant word ends with basic frequency analysis. He saw the most common figure and figured it was probably E.
Then he used context clues. He saw short patterns like E blank 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 E and deduced it was probably the name Elsie. He filled in the gaps, used those letters to decode the much longer message. Am here, Abe Sleeny. It was pure statistical deduction.
And it perfectly illustrates that even when a cipher is novel, the protocol or the inherent statistical distribution is often the fatal weak point. We see this on a much grander scale with the German Enigma machine in WWII. It was a mechanical marvel of rotors, constantly changing the substitution, just astronomical
He
complexity.
was believed to be totally secure because the substitution changed millions of times, but it was broken, famously by Polish cryptologists like Marian Rejewski, who then passed their work to Bletchley Park. What was the flaw they found?
The flaw was in the operational protocol the Germans used. At the time, operators would type the three-letter message key twice at the start of the transmission. It was meant as an error check. But that duplication created a highly exploitable mathematical relationship between the first, second, third, and fourth encrypted letters.
Because the initial rotor settings were known, that predictable pattern allowed them to isolate the day's entire configuration. It reduced the complex machine back to a solvable puzzle.
That one operational blunder gave the cryptanalysts the toehold they needed. It's a remarkable piece of history that stayed classified for decades.
And that history brings us right to the pivotal challenge classical systems could never overcome: secure key exchange. For any of these to work, Alice and Bob have to physically agree on the secret key beforehand. If the key gets intercepted, all communication is useless.
And that failure of key management led directly to the modern revolution, public key cryptography in the 1970s.
The core paradox here is still mind-bending to me. Alice and Bob can securely communicate without ever having met, and everything they exchange, including the encryption key, is public.
It works because the security foundation shifts entirely. Instead of keeping the key secret, the encryption key is made public for anyone to use. But finding the corresponding decryption key is designed to be computationally infeasible.
So security is no longer about secrecy, but about time and computer power.
Precisely. We rely on the inherent difficulty of hard mathematical problems. RSA, for instance, is based entirely on how hard it is to factor very large numbers. You can encrypt easily, but to decrypt, you have to factor that enormous number, which current computers just can't do in a useful time frame. Elgamal relies on the discrete logarithm problem, a similar idea.
This incredible flexibility has to come at a cost, right? I imagine all that hard math slows things down quite a bit.
It absolutely does. Public key algorithms need several orders of magnitude more computation than their symmetric counterparts. That's why we don't use RSA to encrypt a 10-gigabyte file. We only use it to securely exchange a fast, symmetric session key. Then that key is used to encrypt the bulk of the data.
So symmetric systems are still the workhorses, which means they have to be incredibly robust against statistical attacks. And that brings us to Claude Shannon's foundational principles for designing a good crypto system.
Shannon defined two essential properties to defeat statistical analysis: diffusion and confusion. Diffusion means changing just one bit of the plaintext should cause a change in many bits of the ciphertext. It just spreads the statistical patterns out so they can't be easily analyzed.
And confusion.
Confusion is about completely obscuring the statistical relationship between the secret key and the ciphertext. If an attacker can see how the key caused the change, they can work backward. Confusion makes that relationship non-obvious. Both are essential for any modern symmetric cipher.
Okay, moving into the symmetric workhorses. We have to talk about DES, the data encryption standard. It used a Feistel structure over 16 rounds, 64-bit blocks, but with a short 56-bit key.
Right. When DES was standardized, cryptologists like Diffie and Hellman immediately sounded the alarm. That 56-bit key space was just too small. They warned back in 1977 that a specialized machine costing around $20 million could crack DES in about a day.
And that prediction eventually became a reality.
It was. The EFF DES cracker, a purpose-built machine, proved the point, cracking keys with exhaustive search in less than a week. But what's often forgotten is the deeper analytical attack that exposed DES's structural weaknesses even before brute force was efficient.
Ah, you're talking about differential cryptanalysis, which the outline mentioned.
Yes. Differential cryptanalysis was a powerful tool developed in the late 80s. It wasn't about guessing the key, it was about analyzing structural changes in the ciphertext when you make small, controlled changes to the plain text. This showed that DES was fundamentally vulnerable with fewer than 16 rounds. It was a turning point. It showed ciphers could be analyzed for weaknesses, not just brute-forced.
So if 56 bits wasn't enough, the immediate fix seems to be encrypting twice. Double DES. Did that buy them enough time?
Unfortunately, no.
Yeah.
You might assume encrypting twice gives you a search space of 212, but the system was defeated by the meet-in-the-middle attack. An attacker encrypts from one end and decrypts from the other. By meeting in the middle, the search space is massively reduced, giving you the security of only a 57-bit key. Not much better.
So the fix had to be triple DES, encrypting with 3 distinct keys. Which sounds resource-intensive. It seems like the whole mathematical framework had to change for the next generation.
It did. The entire field is built on number theory, specifically modular arithmetic. Every letter, every piece of data is just a number. To perform the complex mixing and manipulation you need for robust encryption, you need specialized mathematical environments.
That's where concepts like finite fields come in, which power modern standards like AES. Why is that operating within a finite field like TextGF so crucial?
It's all about efficiency and predictability in hardware. A finite field is a set of numbers where you can do addition and multiplication, and the result always stays within that closed finite set. For TextGF, every operation involves exactly 8 bits. This makes cryptographic operations incredibly fast and efficient for digital circuits. It ensures the process is both sound and highly optimized.
Before we get to the quantum threat, let's tie this back to a daily application, passwords and salt. What's the mathematical defense against a dictionary attack?
So the standard dictionary attack assumes an attacker gets a file of hashed, encrypted passwords. They can pre-calculate the hashes for every word in the dictionary password 123 and just instantly compare them to the entire file.
Right. It's a fast, simple lookup once the dictionary is built.
Salt destroys that efficiency. Salt is a small, random string of bits, often 12 bits, that gets added to your password before it's hashed. This random value is then stored publicly right alongside the hash.
Wait, if the salt is public, how is it secure?
Because the salt is unique for every single user. To run a dictionary attack, the attacker can't just build one simple hash table. They now have to hash every word in their dictionary with all that's 496 possible salt values. They need 4096 times the storage and 4096 times the computation. It makes a massive pre-computed attack completely infeasible.
Wow. We've gone from simple K-out-free 3 shifts to relying on hard number theory. Let's conclude by looking at the theoretical limits of security. Is there anything that is truly, provably unbreakable?
Yes. The theoretical gold standard is the one-time pad, or OTP. Mathematically, it's the only provably unbreakable crypto system, but only if 3 conditions are met. The key has to be truly random, it has to be as long as the message itself, and crucially, it must never be reused.
The perfect cipher. It was reportedly used on the Washington-Moscow hotline during the Cold War, but if it's unbreakable, why aren't we all using it?
The key management is its Achilles heel. Producing truly random keys of that length is difficult and expensive. Using a pseudo-random generator just destroys the guarantee of security. But the biggest problem is transmitting the key. If your key is the length of your message, you haven't solved the security problem. You've just moved it from the channel to the courier who has to transport this enormous physical key.
Which brings us to the biggest looming threat over every system we've discussed, the quantum horizon.
This is the existential threat to public key cryptography. Quantum computers operate on, linear combinations of states simultaneously. The specific concern here is Shor's algorithm.
And that algorithm completely undermines the mathematical foundation of our modern internet.
It does. Shor's algorithm demonstrates that a functional quantum computer could factor large integers exponentially faster than any classical computer. And since the security of RSA and all factoring-based systems is built entirely on the difficulty of that one problem, a large-scale quantum computer instantly renders them all obsolete.
What a journey. We've tracked cryptography from Caesar's shift cipher, where the whole method was the secret, to Vigeniere's complexity, which relied only on the key being secret, and finally to modern systems like RSA and AES, where the methods are open and the public keys are intentionally public.
And that's the final, wonderful paradox of public key cryptography. We achieve modern digital trust by giving the adversary more information, the full method, and the encryption key. But we're relying on the hope that finding the decryption key is simply too time-consuming, even with the vastest computational power available today.
We are betting everything on computational infeasibility.
Right. Which means the battleground is constantly shifting from cunning code breaking to pure, hard mathematics. If you're curious to explore further, consider this. Our entire digital life, your banking, your emails, is currently betting that number theory stays hard. But if quantum computing arrives before post-quantum algorithms are fully standardized and adopted, the entire basis of digital trust built over the last 50 years just vanishes overnight.